So let me give a brief introduction of Peter. Basically, he has done his PhD at the Institute for Computer Graphics and Vision at the Graz University of Technology, Austria. And after that, he has been a senior scientist there, and also in 2009 to 2013, being the head of the working group at this institute. And basically, after that, in 2015 till today, he's an external lecturer at the Fachhochschule Joanneum, Graz, Austria. And he has been also a scientist at the Austria Institute of Technology, Vienna, in 2015 to 2016. And starting from 2016, he is the deputy head of working group Computer Vision for Augmented Reality Lab at the TU Graz. And we are very happy to have him starting from this month, being a guest professor at our AI Future Lab, AI for EO. And he is one of the core scientists on the topic, one of the three topics, which is reasoning. And like every guest professor, when they join the lab, we will organize a talk with the purpose of introducing the guest scientist to the research environment, and also to stimulate possible collaboration. And today, Peter is about to give a talk titled Dealing with Data-Related Problems, Learning-Based Artificial Intelligence. So Peter, the floor is yours.
So thank you very much for the introduction. I hope you can see my screen because we are exploring some technical issues before. So now I'm working with my backup solution, but I hope that this is still working. What you can see here, I hope that I did a good job considering the corporate identity and the corporate design. So I tried to use the slides templates provided by Tune. Yeah, the main point, as already was said before, considering my background, I'm originally coming from mathematics and then moved under computer science, in particular in the field of computer vision and machine learning. So in this way, I'm typically summarizing my background as visual learning, trying to bring together visual applications and machine learning. And this is also something I would like to talk about today. In particular, I was focusing on two specific topics, which might be also interesting to you. I was also able to talk to several people before, so I tried also to focus on those topics which might be interested for the other colleagues. And in this way, I decided to have the title Dealing with Data-Related Problems in Learning-Based Artificial Intelligence, just so saying that we're not just dealing with machine learning approaches and machine learning algorithms. However, that we also has to deal with specific characteristics of data. And this was really something when I finally was browsing through my research from the last 15 years. It was one of the core topics I was working on. So in this way, I can skip the details. I was just preparing because I did not know how the introduction would be. So everything which was shown here was already told you by Professor Su before, so I can skip this information and then can directly go into my scientific interests. So as I said before, I'm coming from mathematics, so then moved on to applied statistics, and then everything which is related with data mining and data analysis, in particular machine learning and image analysis. So this is very, very theoretical basics. However, in the last years, I moved on to specific kind of applications in life science, in particular medical imagery. Then I'm currently doing a lot of work in plant science. And recently, also in the last 2 or 3 years, also came to the application field of remote sensing, and this way also to Earth observation. And there have been also a lot of cooperations in Austria, particularly with Joanneum research, but also working together with colleagues from BOKU Vienna, where in particular these topics of higher relevance. And now I'm also happy to supervise PhD theses which are going in this specific direction. So also one of the reasons and motivations for me for being in this lab is now really to be able to bring in this kind of expertise to these fields. And this is really what I'm interested in, just to see, I'm keen on to see that all of the topics I've been working on the last 15 years are now really important and interesting for other researchers as well. So this is one of the main reasons I'm finally here. So in this way, I will come to the motivation. So to be fair, the motivation would be not directly related to Earth observation by now, but just based on specific ideas from the applications I was dealing with in the last years. However, they still could show what we are doing. In general, what I would like to summarize at this point is now specific challenges you're dealing with, that we have to deal with in machine learning. The first one for sure is that we have a huge amount of data samples. We're dealing with big data and having data around there, but there's still a problem how to deal with this huge number of samples. The other problem we're dealing with is the high dimensional representations we have. It's not including high dimensional or high resolution images. We also have other applications. Data is stored in high dimensional vectors or matrices or tensors in general. So and also we have to deal with this kind of characteristics of the data. Another point which is often ignored is just that we have a limited memory and computational resources. Just recognized this last week because I have also on my own a number cruncher which is high performant. However, still I was in the problem of running out of memory. So in this case, there's still limitations in terms of computational resources and memory. And also I'm working towards bringing machine learning also on chip, on handheld devices. So it's also important to have approaches and algorithms which are also working with limited resources. Another point which is also often ignored are suboptimal representations. What I've seen, this was the reason why I have data problems in my title, meaning that the people often keen on working on algorithmic level, however ignoring that many problems can be avoided if you're dealing with a better kind of representation. And this is really something which is very important, because if we have a better representation, if we have better prepared data, then many problems are getting much, much easier. Another point, and this would be then the core of these presentations, are ambiguous labels, because typically coming back to high dimensional representations, huge number of data samples, you typically being in some kind of supervised learning setup. This means we have data and labels in parallel, and from this point of view, we need to assign a data point a label. This is typically done by a human. And there we're coming up with specific problems, and I'll just name 3 of them, which is the semantic gap. I will talk about this later on. The large intraclass and small interclass variation, and also the problem of the human machine perception gap. I will explain these points later on. And even though the main goal is to get as automatically as possible, there's still a lot of human effort necessary, in particular for data preparation and labeling. So you can see here, considering machine learning, I typically don't like the term artificial intelligence because it's too general and overused in these times. The many points we have to deal with. However, in this presentation, I would just focus on the problems of ambiguous labels. And for this, I would like to show you some examples what this does mean. The first application I was working on quite a long time was personal identification, which is illustrated here. The main goal is that we have 2 or more overlapping cameras, and the idea would be to re-identify, to find, to localize a person shown in one image and the other one. So in this case, it would be now the task for you. This is typically working much, much better in a direct setup. However, I think it would be not a big deal to find the person shown here on the left side, crossing the image on the right side. So this is a big surprise. So this was not that complicated. However, now we're making the task a little bit more interesting, having exactly the same task. However, our database is larger. So once again, the same question here. We have now the person shown on the left side. Now the question would be, are you able to identify the person on the right side? Just have to look very carefully. And I will show you the solution. So finally, this person is here. So once again, you can see here, it's if you know the answer, then the result is not that surprising anymore. However, what this example should show, if now the number of samples in the database is getting larger, and if the diversity is getting larger, then we are running in several problems, making it harder to find this person in the data set. And if you assume that this database is not just consisting of, let's say, 50 images, but 100, 1,000, 10,000 images, it's clear that this task is not that simple anymore. Then I would like to show you a similar example. Now we're going from image retrieval to 3D model retrieval. So the task here is similar to what we've seen before. The main idea would be, given an image here on the left side, we would like to retrieve a 3D model here on the right side, where the 3D models have different characteristics. We just here have a tabbed map, which is seen here or here. We have really a 3D model with a texture on it, or just a 3D model consisting of a simple grid model. And now once again, the task for you would be to identify which of those models does best fit to the image given on the left side. So, frankly speaking, I'm a little bit tricking you, because in this case, there are two correct answers. And this is once again, I'll be coming up with the term of ambiguity, meaning there is not one-to-one mapping. However, in this case, there could be two correct mappings which are true. And the other point, what you can see here, we have here now a tabbed image, we have here a 3D model with a texture on it. And the main point now is that this mapping is not a single mapping, but we also have different characteristics. And this is really causing some troubles in practice. Then another example, once again, the same thing. We have here, once again, an image on the left side. And now the goal will be once again to identify the correct 3D model on the right side. What you can see here, now representing another problem, is that all of the candidates which are here in our search space are very similar. And I'm tricking you once again, the searched item was not there. So this is also something which can be seen here, besides the the ambiguous mapping. We have also the problem that the samples we're searching for are very similar, causing other problems in practice. In this way, we'll come to the third example I would like to show you, which is fine-grained classification. This is then heavily related to everything which is related to to image segmentation, where we're dealing with very similar problems. And even though I will show you a different application here in this presentation, the main motivation and the main application for this problem was finally to deal with image segmentation. And if you're dealing with fine-grained classification, this means that we would like to distinguish samples of the same category, however, where we have very subtle differences. And here I would show you 3 examples to make this more clear. The first one is here images from the well-known and widely used iris datasets of R.A. Fisher, where the main idea was to identify different kinds of iris flowers just by 2 parameters, the length of the sepal leaves and length of the petal leaves. And here you can see that just from this visual information, it's very hard to distinguish between these 2. Another example which is here is considering, because also this is very ongoing research and people are very interested in this very classifying of birds. And even though these 2 images seem to be rather similar, these 2 images are showing different species. So once again, we have this subtle difference which we have to model. Another example is here from Malaysia, this special kind of piece. Once again, you can see here, if you look on the details, just on here on the head, or this kind of this food, you can see that there are very subtle small differences which are here important to differentiate between these different kinds. And this is another problem we have to deal with, that we have data, we have samples which are very similar in the original representation, ever having different labels. This is another problem we have to deal with. And this brings me now to the 3 points I was mentioning before. The first I would describe as the semantic representation gap. This means that we have to deal with samples with the same label which are not similar. And on the other side, with samples with different labels which are similar. This sounds strange. I also would like to give an example for this one here. This is once again something we saw before. So what we have here, we have an image of a car, we have a 3D model with a car with a texture, we have a depth model of a car. If we're just looking at the original representation, all of these items are totally different. However, as you can see here, they are sharing the same label. Could be a car, could be even the same make. So in this case, having the same label, but the representation, the data itself is not similar. The same can be seen here for the birds. Now having a different view on the bird, in this case of the same species. Even for the view of the bird is a different one. In this case, we have the situation that we have the same species shown in both images. So in this case, we have the problem that the sample that once again the data is not similar. However, we have the same label. Then the example from before, where we have now the same label, the different label with very similar images. And this is another point we have to consider here. And here, the other example from before, once again, 2 very similar images, similar representations, not sharing the same label. So this is the typical semantic representation gap. And even though we're dealing with supervised learning, the main problem is finally that you need a human who is doing this kind of annotation. And often it's not that easy to define this kind of similarities. The next point we have to consider, also was illustrated by the examples from before, is the large intraclass and small interclass variation. Also, I want to illustrate this using an example. So here a class of dogs and a class of birds. And in this case, it might be very simple that we can easily divide and separate the dogs from the birds. However, in this case, even though the image of the birds are quite diverse, all of them are sharing the same label as a dog. However, for some reasons, here for the birds, it's necessary to split them up, which means that here the samples are very similar. The same applies here. However, in this case, they're defining different classes. And this is also something we have to deal with, this large interclass and the small interclass variation, which is not shown in this example very well. And then finally coming to the third point, the human-machine perception point gap, which means that we have to deal with the problem that similarities which are recognized by humans are not similarities which are recognized also by machines. This is something we have to deal with. This can be in some kind of non-linear relations, some hidden correlations, or that just the human perception is not really meeting the mathematically defined matrix. And this is once again an example from before, just seeing here, if we're just talking in this case of color spaces, just taking account RGB color spaces, then for human, these two colors would be similar, these two colors would be similar. However, if we're just taking the representation in an RGB room, this would not make much sense. So this is also one of the reasons why finally these CNNs are working quite good in practice, because we can overcome problems like that. But this is another problem, that humans have to define the labels, humans have to define similarities, which is often not that easy. And this way, I would like to show you two strategies how we can overcome this. Since a little bit late in schedule, so maybe we'll just give you a very brief overview on the first topic, and then we'll go in more detail in the second one, which is newer work, which might be more interesting for you. The first point, how we can address this, is to use a beta metric. And I found this like also this topic, because when I was talking to the other colleagues within the last 2 weeks, we've seen that also other people are interested in this field. So I think it might be interesting to give a short overview also on this topic. In general, in this case, we're talking about novice metric learning. So in the following 2 minutes, I will just give you an impression, what does metric learning mean and why you refer to the whole thing as novice metric learning. In this way, we need just some simple mathematical definitions, starting here with the quadratic Euclidean distance, which does mean nothing else. We have here the difference between the samples and then creating the operation with the dot product for getting this information here. If you're having the non-quadratic distance, you're just taking the square root of this information. So this is just convention. We will see later on why this is important. Because the main point here is now that based on the quadratic Euclidean distance, we can do a minor change, which means that coming from the quadratic distance, we're coming to the lowest distance, which means nothing else than we're including a matrix M at this point, which is nothing else than scaling different directions and dimensions in the theta. This is the reason why we're introducing here the quadratic distance, because we need it here for this representation. And now, the main point in metric learning from a general point of view is to estimate this matrix M such that the data fulfills the properties of a metric. It was shown later on that also the properties of a pseudo-metric, which are less restrictive, are sufficient in this case. And the main point is that this metric, that this matrix is finally representing our task in a better way. And this is very important. This what you can see later on also when having a look on the results. And the main point here, they have two special cases, also explaining the name. The first special case is if this matrix M is just inverse of the covariance matrix of the theta of the samples X, then this is called the Mayanovitz metric, which was introduced, I think, in 1936. And we'll see later on that even using just the Mayanovitz metric is beneficial in practice. And then, if this matrix M is just identity matrix, they have the clean metric. So if just we have here the identity, then this part is missing. But these are the special cases. In particular, the name Mayanovitz metric is coming from the fact that originally it was introduced having the scaling matrix using the inverse covariance matrix. Then in this case, I will just introduce an alternative formulation, which can be seen also in many publications, because writing up the optimization problem is then much easier. What you can see here is now rewriting this term here in the formulation, seeing that now the matrix M can be obtained for the multiplication of matrix L transposed by matrix L. And in this way, we are capturing exactly the same information. And for some reasons, this formulation, which is capturing exactly the same information, is easier for some kind of mathematical optimization problems. And we will also use this later on. One key point, which is interesting here, and which was also paving the way for getting very efficient computation of this matrix, is that we can use so-called pairwise constraints. This means the data is given in form of pairs. We will now explain what this does mean. And the main idea here was that typically, if you're having also this assignment problems from before, we are dealing with multi-class problems, which are typically hard to solve and hard to model. And now the main idea here is that we would like to reformulate this complex multi-class problem to a binary problem. And this is done by this pairwise formulation. In this case, we are just describing two kinds of pairs, similar pairs, that are those pairs sharing the same label, and these similar pairs which are not sharing the same label. This is giving here pair xi, xg having the same label, pair xi, xg not sharing the same label. And this is very interesting because in this way we can assign data points which have nothing in common, a common property, which means they are not similar. And just using this kind of trick, we're finally able to transform a very complex problem into a two-class in a binary problem. And from this point of view, transferring this multi-class problem into a pairwise problem is making our task much easier. So finally, we're ending up in this kind of formulation, what we would like to train. As you can see here, in this case, I'm now using this formulation using the matrix L, just because it's easier to write and saving space. And the main idea is just that we would like to have here, we would like to have that similar pairs should have a small distance, and dissimilar pairs should have a large distance. And this can be formulated in a very easy way, as you can see here. We have just a minimization problem. We would like to have here now the transform distance of similar pairs, which are given here, and the transform distance of the dissimilar pairs. And to minimize this one here, you can see here, we would like to have very small sum here. And to minimize the overall term, since this is a negative, this is a minus, we would like to have this term as large as possible. So this is a very simple problem, how this can be minimized. However, there are shortcomings. The first shortcoming is very clear. If we just take any minus into account here, which means that minimizing this formulation is then really highly biased by minimizing the dissimilar pairs, which means making dissimilar pairs even more dissimilar, then our job is done. So we don't have to care anymore about the similar pairs. So this is really a big drawback, having just this representation in mind. And the other point is, for solving this problem, we're coming up with very complex iterative schemes, which are not very efficient in practice. So in this case, our approach to deal with these specific problems is to really take into account the constraints given by the task. So we don't have to solve every problem of the world, but typically in practice, this also applies for our problems in remote sensing and Earth observation with very specific tasks. Our data has very specific characteristics, so we don't have to deal with all of these problems. So exploiting the constraints given by the task, exploiting the constraints given by the data. In this case, once again, I would emphasize the term data, which is as important, if not even more important than just algorithm. And in this case, what we tried to deal with this problem was to find an efficient and, in the best case, enclosed form solution. In particular, where it is, to avoid these computationally expensive methods. And what's really shown is that it's really possible for coming up with a closed form solution where we can avoid these iterative approaches. And finally, one point was really to say that we're coming up with mathematically meaningful constraints. Just say, okay, if we have the constraints, then it should be meaningful in terms of our problem. However, in our case, also selected that we can reduce the mathematical complexity of the problem, making it easier to solve. Another point is to exploit the statistical information, which is naturally given by the data. And the first point is really relaxing the hard problems, because the main point why we're finally ending up in this kind of complex iterative approaches is that we're trying to guarantee constraints which are not necessary in practice. So in this case, relaxing the problem, ignoring specific constraints, making the problem much, much easier. So I will skip the details here for the different approaches. I will just go back to the overview just to have an eye on the schedule. And coming back to the results we're finally getting here. So if you're interested, I also prepared just an overview slide giving the details here. However, there have been different approaches which have been exploited, and now we'll just focus how these specific formulations can be meaningful in practice. And finally, we're coming up with two main points. The first point is that using this kind of metrics, we get significantly better results. And the other point is that the computation of the metrics is much, much faster. So this is very, very nice that both of these aspects can be covered within the same kind of algorithms. And this I would like to illustrate you with short examples. Here I'm showing examples for image retrieval, and in this case I'm showing you a so-called CMC curve. For those of you who are not familiar with this kind of curve, I will just briefly explain it. We're just taking this point here with an image retrieval problem. In our case, there are 300 images in the database. And here this point 50, 55 means that in 55% of all search requests, the searched item was within the first 50 ranks. So this is terrible. However, at this point, it was a very good result. Or this point 155 as 75 means that in 75% of all cases, the searched item was within the first 100 ranks. So it's just from a classification point of view, this is terrible. But what is important for you? This is now the result which was obtained using the Euclidean distance. And now you can see here is the improvement we're getting by using a different metric, which means we have the same problem. We have the same data representation. The only thing which was changed here was just a different metric. What you can see here, that we're now reaching or starting from a point 55 up to 95 here for 50. At 100 from 75 to 98. And this was just because of using a different metric. It really makes very clear that using a meaningful metric is very important. This can also be seen here from the results in terms of hard facts. We can see here these are the approaches I skipped before, is KISME, BRDC, and IML. We can see that compared to other approaches, we get much better results. This is the first point. And the second point, which can be seen here, the computation time is very small. Whereas we are doing the whole thing just in fractions of seconds, other approaches are needing multiple minutes or even an hour for doing the computation. So what we see here is we're getting much better results in drastically reduced computational time. And something which might be important, therefore is also highlighted in bold here, is that just using the Mayanovitz metric, which is doing nothing else than just a Whiting transformation, meaning to use an scaling using the inverse covariance matrix, finally gives similar results as all of these metric approaches, however, more or less in zero time. So this was very interesting. What you can see from this table, significant speed up and significant improvement. Overcoming the shortcomings, this way up to now we are dealing with handcrafted features. We cannot deal very well with if the data is a little bit more heterogeneous, which is the case in practice. So the solution for dealing with these problems was then to jointly using the representation and the metric using Gaussian neural network, and in addition also exploiting the geometric constraints. And here you can see once again a summary of the other approaches here. And now the main point was exactly these ideas can be then also be extended to neural networks. And this is something I'm very proud of, that ideas we have been developing 10 years ago now also found their way to modern learning techniques. And in particular, the work I was doing together with my PhD student, Alexander Gramner, was very successful because in this case, learning a metric for neural networks really showed that they got a significant improvement. And in this way, the idea and the goal was to work now on model retrieval, which was exactly what we've seen before, that we're giving an image and would like to find the model here. And the main idea, will not go into details here, was once again to learn a metric in a common representation space using and CNN, and in this way we have been able to get significant improvement. If we have further work once again also to come up with a better intermediate solution representing these different characteristics. And finally, just giving a very short overview here. So if interested, we can talk about this later on in more detail. Can be also seen that now just having this better metric, we can get a significant better result. And once again, this accurate top 1, accurate top 10 is once again summarizing what I've telling you before, considering the CMC curves. We can now see that starting from a classification result of 90%, we are able to come up to 65%. From 46% for top 10, we're going up to 89. So in this case, there have been several aspects. First thing was that using a better intermediate representation, common embedding, giving a better result, and the other point was having a metric. And just to summarize, the main point is that all of these ideas we've been working on have a joint theoretical foundation. I was also writing up the whole thing, the journal paper. We can apply the whole thing for different tasks, and which is very important, these ideas are also extendable for deep learning. And one of the main points which I would like to talk here is how these ideas can now be also been beneficial here too. As I said before, one of the points would be interested in and working on this common embeddings of different representations, which can be also seen in the context of concept spaces, really trying to represent different representations in a joint formulation. In this way, but also something we have shown, if using a widely chosen metric, we can drastically reduce the computational effort, and we can also improve the classification segmentation results. And as I said before, main motivation for me is now to use this kind of ideas here, in particular for semantic segmentation. Okay, then just having an eye on schedule, we'll just give a very brief introduction to the second strategy, which is now neural network parameter training or tuning, which means that now coming from ideas which are basing on old theory, we're now also coming to the new aspects. If you're talking about neural network optimization, there are typically many ways for doing so. However, an important parameter which is often ignored is the proper choice of the non-linearity. What you can see here, because we've been talking about this last week, that there are specific activation functions required for specific tasks. All the time there have been different activation functions introduced, starting from this kind of squashing functions, which are sigmoid or Dangles Hyperbolicus. Later on, Relo and Swish have been introduced, all of them having specific characteristics. However, typically for most particular deep learning approaches, Relo is used. The main reason for that is it's easy to understand and efficient to compute, because if you're talking about backpropagation algorithm, computing the gradients are very easy, taking this into account. However, also other functions might be used and might be beneficial in practice. And this is the second one I was focusing on, to see how we can use a better activation function for getting better results. And this I would like to show you a very simple example taken from a recent paper. You can see here the goal is to find the separation from the red points from the blue points with a very simple network. And you can see here, just using a Relo, this is not possible. If you have a more complex system, more complex network, then you can do this. This simple example, this is not working. However, with the approach we were introducing called L-star Relo, even having the same architecture, but just a different activation function, allowed us to get much better results. This is not possible using other similar comparative approaches. And now what I would like to give you very briefly, just an introduction to these two approaches. You can see here this approach was obtained manually, where this was trained automatically from data. And once again, the main motivation, main idea is to say, just changing a simple parameter allows us to make the model complexity much smaller, and in this way much more efficient in practice. And in this way, we came up a paper from 2016. You see, in particular for this Finegrained classification, in our case, also coming back to semantic segmentation, we need also to model the degree of absence. In our case, coming back to Relo, which means that we have this positive part, which is preserving information, and all negative values are just mapped to 0. So we're using all of this negative information. And here it was summarized that the activation function should have specific characteristics. It should be strictly monotonically increasing and uniformly continuous. This was exactly what Clevert was enforcing, and I will show you a few examples which are well known. The first is Relo, which is typically used. You can see here, this is definitely not monotonically increasing, so not sufficient in our case. Then you have Elo, which is here in the positive part, similar to Relo, where we're saturating in the negative part. So once again, this is not uniformly increasing. However, it would be uniformly continuous. However, here leaky Relo, which has this small slope in the negative part, is finally sufficient in this case and giving us the results we would like to have. So in this case, we would like to focus on the leaky Relo, which is just defined. That way we have positive values are mapped by identity, and the negative values are mapped by a small parameter alpha here. And here the main point is that this parameter can be chosen data dependently. And what we found out in this specific work was now that we have functions which have the same Lipschitz constant, which is describing the maximum gradient within the function, have similar properties. So this way, the idea was now to select the simplest one, in this case, the Leaky Relo. That was the reason why we came up with this theory, because we have Lipschitz Leaky Relo. So the main idea was just to say that we're using a meaningful, properly initialized Leaky Relo for this specific purpose. Then just having a look on the time, so we'll just go to the results which can be seen here. We've been dealing with two specific characteristics: on coarse-grained visualization, where the data is well separable, and a fine-grained visual classification, where the data is not that good separable. And we've seen that in the simple task, the choice of the activation function is not that relevant. So more or less all of these results are the same. However, if we go into the fine-grained problem, where we have to model the subtle differences, then you can see that just using a properly initialized Leaky Relo gives significant better results compared to all other approaches which are typically used. And this is something which was very important, just to see that just changing a simple parameter is giving much, much better results. Here you can also see that these results are also covered by multiple runs in a very good way. However, then I will come just to the last point, to be not too long, which is then the last approach I would briefly describe, is now learning these piecewise activation functions. What we've seen before is what we have demonstrated, that using this alpha parameter in a meaningful way gets significant better results. However, we have to do a brute force parameter evaluation for getting this parameter, which was assumed, considering the reviewers, this is a typical way and is allowed. However, we need multiple runs for all of doing these evaluations. Other approaches like Bearish are failing in practice, because the main point is that here in this case an gradient-based optimization is used. And if you're not initializing the approach using or close to the optimal solution, the whole thing is failing. So neither manual selecting nor desensitization is meaningful. So we came up with a solution of meta-heuristic optimization, which is based on particular swarm optimization, which ensures us finally a global optimal solution. And our idea here was now to use this particular swarm optimization approach to estimate this parameter from the data automatically without any human input. What you can see here is, in this case, please focus on the column of GPSO, that we have been evaluating two different approaches, that where LPSO is working quite good for simplex problems, is not working that good for more complex problems. However, what you can see here, this is the optimal slope, which was estimated manually, and using GPSO, really this information can be covered very well. This is then also represented by the experimental results. We can see for sure having the same slope, we're finally also getting similar results. And once again, which is very important here, is where our approach using this BSO is giving results close or even better than the optimal one. Another approach, which is using this automatic estimation, is somehow not failing, but not working that good. However, just to come to a conclusion and to an end, what I wanted to show here is that the proper choice of activation function can be very important, in particular if you're dealing with this kind of fine-grained problems. In this way, we propose to use piecewise linear functions because they're easy to understand and very efficient to compute. We need only to set one parameter. This parameter, I skip this part because it would have used too much time. It's important but critical, which means that there's typically a range where we have to define the parameter, finally ending up in a working solution. In L-star Relo, this parameter can be estimated empirically from the data, and for S-star Relo, this can be estimated really learned from the data, which gives us a visual speed of a factor 10. This is really something which is very nice. In our case, once again, coming back to what can we do here at TUM, main motivation, once again, is to try to improve image classification, in particular segmentation problems. And this is something also ongoing work is showing, that using this kind of activation function can give us better results. And the other point, which is as important, that in this way also the model complexity can be reduced, meaning that we can get the same accuracy on a reduced model complexity, finally give us the chance for being more efficient. So in this case, the end, many thanks to for all of the people who have been involved in this work. Typically, if having this wide range of applications, then this is not a single work. So in particular, thanks to all of the students and collaborators who have been involved. And then thank you for your attention. Info was a little bit too long. Oh, thank you very much.
Thank you, Peter, for this illustrative compilation of the key AI challenges and for sharing your related research highlights. Now is the turn for our audience to ask questions or to give comments. Please, if you have any, write the Q letter in the chat and I will give you the floor. We have still some more minutes for that.
So maybe I start, Peter. It's very fascinating to see all the nice work you have done in the vision, let's say, direction. And now you are joining our lab, which has rather a focus on remote sensing data from bird eye, so to say. And what are the, let's say, directions where you see great potentials that we can basically benefit from your previous experience in computer vision? And what are your main interests in this regard?
Yeah, this in particular points I did not mention in this presentation because I was told before that we recorded and then put online. So I didn't want to talk about ongoing work in a public audience. So maybe this would be then things we can talk on later on, because I prepared additional slides which should illustrate also the work I've already done in this field and how these ideas could be beneficial. But overall, I would say the main point would be, what I said before, was also try to say in this outlook, is that what we've seen that in many tasks we're dealing with some kind of semantic segmentation, with classification, and I also was doing work in particular together with the colleagues from Econ Research in this field, considering satellite imagery. So in this way, many of these ideas can be applied there. And what we've recognized is that the same also applies for medicine, that this kind of data has specific characteristics so that off-the-shelf approaches cannot be directly used. So we have, once again, to be data dependent, we have to be task dependent and have really to take care about this. But this is something maybe which I would like then discuss in private in another recorded session. The other point in general is what also said was considering and talking about improving approaches and reducing computational complexity, because even though I'm having now a very powerful computer, I'm seeing that if just using off-the-shelf approaches, I'm running out of memory and I cannot run this anymore. So this was also particularly taking account the satellite images and other airborne images which have a high resolution. I'm dealing also with images taken from Meteorone, which are up to 6100 gigapixels. So in this case, it's also important to have an eye on computational resources. And I would say that, in particular, we've seen from before that there's a dramatic speed up and reduction of model complexity. And I would say if you have to deal with this huge amount of data, also preserving the accuracy, however, and a reduced computational effort could be very beneficial also in this context.
Thank you.
Okay, we have here one more question from Professor Koho Pillai. She said, many thanks for your presentation. Is it also possible to minimize data needs in your approach?
What do you mean with minimize?
Maybe not.
I can just explain. I'm actually the ethics person in the lab, as you probably know. And I was asked, one of the recommendations from the European Union is data minimization as a part of the ethical requirements for any application which requires a lot of data, to make efforts to minimize data. So I was wondering if with your approach, it's possible to minimize the needed data to acquire the same level of accuracy.
Yeah, this was in particular not covered in this presentation, but this was because I had several topics prepared and finally decided to just cover these two topics. But this would have been another part which I skipped. So the main point is, this was also when I started with machine learning, I came up with online learning exactly for the same reason. The first thing was, once again, we had limited computational resources, and the second point, we had limited amount of data. And there was one important part, was just how we can drastically reduce the amount of data, in particular how the amount of labeled data. So one of the works that was also one of the directions that was following during the last years was everything which was related to few-shot learning, to semi-supervised learning. And there was one work we finally ended up that just using a single labeled data point finally gave us exactly the same accuracy as our competitors, which have been using 10,000, 100,000 of samples, labeled samples. So from this point of view, and it was also something we have written the proposal for my work within this lab, was also that we are working on this direction of semi-supervised versus some kind of reinforcement learning in some kind of automatic modeling, with the goal of reducing the amount of data, in particular the amount of labeled data, because also something was saying before, is that labels often assigned by humans, and the main problem we're dealing with, because I currently also have this another problem, where I have to annoy the colleague all the time for annotating new data, and in this way it would be beneficial for reduce the annotation on the human effort. So to make a long story short, this is not possible by the topics I presented here, but this would be possible by topics I skipped for time reasons. But if you're interested, we can talk about this later on in more detail.
Yes, I'm very much interested. So I will contact you because I have several follow-up questions. But yeah, thank you very much for a very interesting presentation.
Oh, we would be very happy about this. And yeah, the main point was, yeah, I was just a little bit scared about what to finally select, and finally I think I had prepared 200 slides and that you were able to present 50 of them, which was even maybe too much for this short time frame. However, yeah, I would be very happy to talk to you later on.
Thank you.
Okay, due to time, I think it's time to give this session as close. Thank you very much, Peter, for your nice presentation. Thanks all the audience for being here today. We wish you from now a nice weekend, and I hope we meet again in the next seminar. Bye-bye.
Also, thank you very much.